All right, so let's go through this. So all the reactions that we do in this class, except for radical chemistry, involve electrophiles and nucleophiles, right, or acids and bases. Okay, and so in this case, we have an electrophile and we have a nucleophile. We can identify what molecule is going to act as the electrophile, what molecule will act as a nucleophile.
The oxygen from the NaOH is going to be the nucleophile.
Okay.
And we have two electrophiles, chlorine and bromine.
Right. So as Kavi said, right, we have sodium hydroxide, which is going to be acting as the nucleophile. Sodium hydroxide is just the basic form of water, right, the deprotonated form of water. So we would expect this oxygen to have much more electron density than just regular water. Okay, and then the chlorobromide is going to be the electrophile. And on this, we have two electrophilic centers, right? Those two carbons are going to both be electrophilic. Right, so in terms of a first step, what is a reasonable first step for the mechanism? Right, we have our two reaction partners.
The oxygen bonds to the carbon next to chlorine, and the chlorine is picked off in the leaving.
Okay, so we can add the oxygen to that carbon. Is there another option that we have?
We could add one carbon.
Good, so we could also add the oxygen to this carbon. So both of those carbons are electrophilic. Which of those two is probably going to be a faster reaction? How many people think addition to this carbon will be faster? Okay, why? Anybody?
Because chlorine wants to get out quicker
Okay.
because of the big shell it has.
Bigger than
It's a
bromine?
better living group.
It's a better leaving group than bromine?
Maybe. That's my idea.
I'm just asking.
Yeah.
Yeah? Okay. Anybody else want to offer something?
There's a stronger dipole towards chlorine, so that carbon's going to be more positive.
Okay, so we can say that there is a stronger dipole between carbon and chlorine than there is between carbon and bromine, right? Chlorine is going to be more electronegative than bromine. And so we could, say kinetically, right, this oxygen might be a little more attracted to this carbon, right? A little less attracted to that carbon. In terms of leaving group ability, which of those is a better leaving group, chlorine or bromine?
I said bromine is a better leaving group.
Why?
Since it's the electrons it's bonded with are farther shell.
Good.
Or
Yeah.
polarizability, is that the right word?
Awesome. Yeah. So if we think about the size of these ions, right, we have our chlorine, we can compare that to fluorine, right? And then over here we have bromine, right? And so the two electrons in the outer shell of bromine, the anionic part of the bromine, they can get farther apart and say this is more polarizable. Right? And so that's going to be a more stable anion when it forms. So as a result, right, so Rebecca, you're right that this is a much more polarized carbon, but because that's a better leaving group, that's going to be the carbon that probably reacts first. Okay? So we'll show that addition. We're going to do an SN2 reaction. We'll go over how to choose SN1 versus SN2 today. And then we still have hydroxide and water flows around. All right, so that's going to be our first intermediate. What's something reasonable that could happen next? There's several things that can happen. Where do we go from here?
Could the oxygen from the OH attach to the other carbon then, other chlorine?
So that's one option, right? So we can take our hydroxide add that to the other carbon, kick out the chlorine. Down here. Right, and we create this aromatic diol. Okay, that's one option. We'll see that product form, all right, but this is probably not going to be the major product. All right, so when you think of another step that could happen here, probably faster than substitution, what are the fastest types of reactions you know in terms of kinetics?
Tying,
What's that?
ion,
So we're not going to form an we're not going to form an ion. You're on the right track. So that would be an SN1 where the chlorine just leaves, right, and form a carbocation. Is that what you're?
No, I wanted to find the group minus plus the no, there's nothing else.
Yeah. So there's a sodium ion here that we're not really tracking, but it's around. So in terms of reaction rate, kinetics, right, and things happening quickly, what are the fastest types of reactions? What are the easiest types of reactions to accomplish?
Acid bases.
Sorry, somebody say it.
Acid.
Yeah, acid-base reactions, good, right? So when you look at what we have in the flask right now, what's the acid-base reaction that would occur?
the hydrogen from the alcohol is gonna get taken by the hydroxide.
Excellent. Right, so we're going to form, let me draw this over here. Right, so remember, acid-base reactions are always going to be really fast because to pluck a proton off of a molecule, the orbitals that you have to interact with to grab that proton are always on the outside of the molecule, right? So the sigma star orbital of that alcohol group is sticking up on the other side of hydrogen, so it's going to be pretty easy for a hydroxide just to kind of float by and pick that proton up. Right. Thermodynamically, we might not be forming very much of it, right? So the EQ of this reaction is about 1, meaning that for every one of these we form, we're probably going to have one of those left over. Okay, but that's all right. All right, as long as we can form a little bit of this, then the next reaction is going to be really fast. All right, so we formed the second intermediate. What are we going to do with that?
Move the oxygen bond to the carbon by the chlorine and get the chlorine.
Awesome, right? So at this point, we have the option of taking a hydroxide from outside and doing a substitution on the chloride, right? Or using this oxygen and doing a substitution on the chloride. Why would this oxygen be a better choice? That's what you were suggesting, right? Yeah. So there might be some thermodynamic drive to that, right? That you're making a somewhat stable 5-membered ring. But I would say that's not I think maybe kinetically why that would be the better choice.
It's a stronger nuclear.
Do you get stabilization from like resonance?
No, unfortunately resonance isn't going to play here because the oxygen, there's a sp3 carbon there, right? So we can't, there's no conjugation.
It's a better nucleophile. Oh, sorry.
Is it gonna be easier for the oxygen to actually like make contact with that carbon rather than the hydroxide reaching into there? Is it harder?
Yeah. So think of it like this. So Cal, if you and I just went out into the quad and we were blindfolded, right, and we were just running around, how often would we bump into each other? Probably not very
No.
often, right? It's a pretty big quad, yeah. If we went out to the quad, we were blindfolded, but we had like just a 10-foot piece of rope between us. How often would we bump into each other?
More often.
Pretty often, right? So we can say that this is just as nucleophilic as that, right? But this oxygen is always right there, right? It doesn't have to find that carbon. It's attached to the same molecule. And so really all it has to do is lean over, interact with that orbital, and kick out the chlorine, right? That's not to say that this can't form, right? It's just that this will happen much faster because the nucleophile is always present. Yeah.
So is that a demo that we could do like in real time?
Sure.
Probably gonna go do that after class with me.
I can videotape you guys. It'll be good.
As long as we're blindfolded as well. It shouldn't be-
Right, and so that's going to get us probably to our major product. This reaction. Right, questions about this? Right, so each step of this mechanism hopefully should make sense, right? It should be, I mean, you can look at these mechanisms and you can see, right, when we draw mechanisms, there are multiple paths that we can go down, but only one path is the most likely. And hopefully you can rationalize why each step of this mechanism happens the way that it does, and why we would form that product. Okay, so we're going to talk about this today. Particularly, we're going to focus on substitution SN1 versus SN2, and we're going to be looking at how the structure, how the composition of the molecules that we're using influence that substitution. So compare SN1 and SN2, and we're going to start by looking at how the electrophile is going to affect the pathway, the specific pathway. Right, so just a reminder, the 1 of SN1 means that that reaction is unimolecular. And the 2 means that reaction is bimolecular. Right, so let's take a look first at SN2 reactions and try to understand them from an orbital perspective. What's going on? So just really quickly draw an SN2 reaction between this nucleophile and electrophile. Just see what you get. so just looking at the front row, it looks like everybody's kind of on the same page. So product that we would get should look like that. Right, so in the cyanide, it's the carbon, that's the nucleophilic atom, right? And then the carbon of 1-bromopropane, that's the electrophilic atom. Right? In this step, in this mechanism, taking electrons on the carbon, it's an SN2, right? Both of those things, all 4 of those electrons are moving at the same time, right? So we're making a new carbon-carbon bond. At the same time, we're breaking a carbon-bromine sigma bond. Right? In terms of the orbitals that have to interact in order for this to take place, what is the HOMO, what is the LUMO? What orbital is donating electrons, what orbital is accepting electrons?
The HOMO would be the sp orbital of the cyanide.
Excellent. Right, so the electrons on the nucleophile are in an sp orbital, so that'd be sp non-bonding orbital cyanide. Right, so that's where the electrons are coming from, or that's the orbital that the nucleophilic electrons are housed in. And how do they have to interact with the electrophile? What are they overlapping with? Remember, we're breaking a carbon-bromine sigma bond.
The sigma star or antibonding orbital of the carbon-bromine.
Excellent. So the carbon-bromine sigma antibonding orbital. Right, so we can draw those out. Right, and so this allows us to see how these molecules have to approach each other in order for that substitution to take place. Right, so in SN2 reactions, right, the nucleophile has to come in from the backside of the electrophile. Right, whichever way the leaving group is pointed, right, the nucleophile has to come in from the opposite side. Right, and we refer to this as backside attack. We also have to remember that they're on this same carbon, right? There are 2 other atoms, just hydrogens that we're not showing. So there are always going to be 4 things on that carbon. Right, so those are going to be orbital interactions in an SN2 reaction. Questions about this so far? Okay. Let's look at SN1. so let's see if you can figure out the substitution product for this reaction. Right, make sure it's a stable product. So if you get to a intermediate that's protonated, has an extra proton or a positive charge, think about how you can remove that proton. Right, you want to get to a stable neutral product. So you gotta remove that proton, right? That's in here. How many people have the mechanism drawn out? All right, so where do we start with the mechanism? Who wants to SN1 offer a step there?
Well, carbon cation.
So,
Carbon cation, is that what it's called?
it's not called that. I understand what you're
Well,
saying.
the leaving group leaves.
Good, so the iodine halide leaving group leaves. All right, second step.
The oxygen from the NaOH goes positive charge carbon.
Excellent, right? So we formed the actual electrophile in the reaction, right? The carbocation. And so the methanol is going to act as the nucleophile. Oxygen will add to the carbon, make a carbon-oxygen bond. Right? We still have an extra proton on that methanol. That proton comes with it. So what's the last step then in this mechanism?
You could use the oxygen from the methoxy to take off the proton.
Right? So we just use another methanol molecule, and that's going to act as a base, pull the proton off, and that will get us to our product. Right? That's going to be okay, so let's talk about any questions on this mechanism. Okay. So you can see the actual substitution is, like we learned the other day, the actual substitution is two steps, right? The leaving group leaves, right? And then the nucleophile comes in. Just so happens in this case, the nucleophile has a proton on it that we have to pull off in a third step. Okay. Let's talk about orbitals, all right? First step, it's just the electrophile, right? This is what makes this an SN1 reaction. This is the rate limiting step of the reaction. Right? And we're not going to really talk about the orbitals involved in this rate limiting step because we're just breaking a bond. We're not making any bonds. All right? To understand the SN1 mechanism a little better, it helps to understand the orbitals around this carbocation and the shape of this carbocation. Right? So we're looking at this from a planar view. We kind of turn this on its side. hopefully everybody realizes that this is going to be an sp2 center, trigonal planar, so all 4 of those carbons are going to be all in one plane, right? And then the positive charge is going to be represented by an empty p orbital. Okay. And so this is where our nucleophile starts to come into play. Right, so this is where we want to talk about the HOMO and the LUMO of this step, the bond formation. So what is the HOMO going to be? What's the highest occupied molecular orbital? What orbital are the electrons coming from?
The opposite of that, the origin.
So what orbital?
The SP group.
SP. What's the hybridization of oxygen? Evan?
SP3.
SP3, yeah. Right, so this is going to be SP3 non-bonding. Right, on the oxygen of methanol. And then in terms of the LUMO, yeah,
Would be the p orbital on carbon.
excellent. Right, so that's going to be the empty p orbital on carbon of the electrophile. Right, so thinking about how these two things have to approach each other, how, what should that look like, or what is that going to look like? Right, so particularly contrasting this to the SN2 reaction, right? There's only one direction that these two molecules can meet up, right? Because these two orbitals have to interact, and that antibonding orbital is always going to be on the back side of the electrophilic center. So what are our options here? Yeah.
You can approach from the top or the bottom.
Excellent, right? So we have 2 lobes of that p orbital, so that nucleophile can come in either from the top face, right, or from the bottom face. And we'll see later on that that's going to play a role in the stereochemistry of the product, right? Here we're not creating a chiral center, so we don't have to worry about it, right? But if we were, hopefully you can understand how we would create a mixture of enantiomers, right? If we add it to one face or if we add it to the other face. Same principle as adding to a carbonyl, right? Making a chiral center from a carbonyl. All right, questions about this? Okay. All right, so let's think about how the structure of the electrophile and the shape of the carbon skeleton of the electrophile is going to influence substitution. Get rid of this. Yeah. All right, so I'll just give you some terminology here. All right, so just like we can qualify alcohols and amines with primary, secondary, and tertiary nomenclature, we can do that with our electrophiles as well. Right, so that X is the leaving group, right? Put the CH3 over here. So we can call this a methyl electrophile, or if X is a halide, a methyl bromide, right? If we have one carbon group and two hydrogens, that will be primary, two carbon groups and one hydrogen, that will be secondary, right? And then tertiary is going to have three carbon groups. All right, so if we right, if you haven't drawn an energy diagram yet, put that down because we're going to look at the energy. Right, and we're going to just look at a really simple system and compare the energies. Just looking at SN2. Right, we're going to see how the electrophile is going to affect the outcome or the course of the SN2 reaction. Right, so this is going to be our base reaction. Right, we're going to take a methyl bromide and we're going to treat it with sodium hydroxide or some hydroxide salt. And that's going to give us methanol, or methyl alcohol. All right, and this is a one-step mechanism. All right, so we'll say that that is going to be, and we'll draw that just a little bit lower. Actually. All right, that's what the energy diagram of the reaction looks like. Okay, we can even, if we wanted to, we can show the transition state for this reaction. Right, as the oxygen is adding to the carbon, right, the bromine is leaving the carbon, right? So we're showing the bond that's being made as a dotted line, right, and the bond that's being broken as a dotted line. And then those three hydrogens are kind of arranged as a kind of a plane right in between them. Right, everybody sees that? As a reminder, remember that this is the orbital that hydroxide has to interact with. So if we change this electrophile to a secondary electrophile, right, we'll keep the same leaving group. All we're doing is just adding another carbon. These hydrogens are still there, and then our hydroxide is still going to be the nucleophile. Right, how is this reaction going to compare to the reaction with the primary electrophile? Energetically, what's going to change?
It'll be slightly harder to reach the orbital.
Okay, so how will that manifest in the energy diagram?
A higher peak.
Right. Thermodynamics, will that change? No, right? We're making the same bonds and breaking the same bonds, right? Up here, we're breaking a carbon-bromine bond, same as down here. Up here, we're making a carbon-oxygen bond, same as down here. So thermodynamically, right, the energy of the starting materials and products shouldn't be any different, right? The only difference is the ability of that nucleophile to actually reach the electrophile, right? There's a methyl group here, more cabbage around that electrophilic center, so it's gonna be harder for that oxygen to actually maneuver in, get into, and interact with that orbital. And so that's going to play out with a higher activation energy. Right, what about a tertiary or secondary electrophile? Right, so secondary electrophile, we're gonna have, say, 2 methyl groups and 1 hydrogen. How will addition to the secondary electrophile compare to methyl and primary?
It's gonna make it harder again.
Yeah, it's gonna make it harder, right? We're putting even more stuff around that center that the nucleophile needs to interact with, right? So it's gonna take more energy for it to maneuver past those methyl groups and actually interact with the antibonding orbital. Right, so that would be an even higher activation energy. Right, and hopefully you can rationalize that the tertiary electrophile, right, that's going to be even higher. Right, so what this means is that SN2 reactions don't happen with every electrophile. Right? So SN2 reactions on methyl electrophiles, excellent. Really, really fast. Right? You can take water and mix it with methyl bromide, and those are going to react pretty exothermically, pretty quickly. Right? Primary electrophile is also really good at doing SN2 chemistry. Right? Secondary electrophiles, it's complicated. Depends upon other factors in that structure, right? So that they can happen, moderate rate, right? But like I said, it depends upon other structural factors. And then once we get to tertiary electrophiles, SN2 reactions are not possible on most tertiary electrophiles. Okay? The trend for SN1 is going to be almost exactly opposite. Right, where SN1 reactions will happen really well with a lot of tertiary electrophiles. Okay, they can happen, or that pathway can occur on secondary electrophiles, but primary and methyl electrophiles will not undergo SN1 reactions. Yeah.
So this might be getting ahead of what we're doing now, so if it is, just say so. But if it's, does that only matter if like the if that's extra methyls coming off, or like if that it has to be carbons coming off of the electrophilic carbon, or like what if it's like some other substitution?
Sure. So we're thinking mostly about carbon. If there are other substituents like oxygen or nitrogen, because those atoms have electrons on them, those electrons will play a role in SN1 versus SN2. Right? Particularly if we have something, right, if we had something like this, right? This is not very stable because the oxygen electrons will fall down and will kick out the chloride. And So when we're talking about primary, secondary, tertiary, we're really referring to the number of carbons versus the number of hydrogens around
Okay.
that center.
Makes sense.
Other questions? Okay, is that clock accurate?
Yeah.
Yes.
We'll end there for today. On Monday, we're going to get into SN1 reactions a little more and also break into some elimination